In the hours before dawn, the rocket stands in the floodlights. It has been standing here for days, rolled out from the vehicle assembly building on the massive crawler transporter that moved it at less than 2 kilometers per hour along the crawlerway. The whole journey taking most of a day. The rocket held vertical throughout it, the service structure rising around it as it was positioned on the pad. Since then, the crews have been working, connecting the umbilicals that will feed propellant and coolant and electrical power to the rocket until the moment of launch, pressurizing the systems, running the checkouts, working through the checklist. That is itself the accumulated wisdom of every launch attempt and every anomaly investigation and every lesson learned since the first rockets were built and fired. The rocket stands in the floodlights and the steam vents. The steam is not from the engines. The engines are not running. The steam is the visible exhalation of cryogenic propellant, liquid oxygen at minus 183 degrees Celsius, liquid hydrogen at minus 253 degrees, boiling off at the edges of imperfect insulation, the extremely cold propellant chilling the surrounding air and the structures around it, the moisture in the Florida night air, condensing and then evaporating in thin, drifting clouds that the floodlights catch and make luminous. If this kind of story is how you end your nights, please subscribe right now so you never miss one. Hit the like button. It means a great deal to this channel. And drop a comment telling us where in the world you are watching from and what time it is there. We love knowing who is with us. Now, let's go to the pad. The rocket is the largest machine human beings build with the intention of making it leave the Earth. Not the largest machine we build. There are larger structures, larger ships, larger buildings. But the largest machine we build specifically to escape this planet, to push against its gravity with enough force to rise through the atmosphere and reach the speed at which the curvature of the Earth becomes the trajectory, the speed at which falling becomes orbit, the speed at which a human being or a satellite or a space telescope can be placed somewhere where it can do work that cannot be done from the ground. At the top of the rocket, under the aerodynamic fairing or the capsule that protects it from the aerodynamic heating of ascent, is the payload, the thing the rocket exists to carry, a satellite, a space probe, and a crew in their capsule. The payload is typically a fraction of the rocket's total mass at launch, often less than 5%, sometimes much less. The vast majority of what sits on this pad tonight is propellant, and structure to hold the propellant, and engines to burn it. The countdown is running, not audibly from here, not yet. The clock ticks in the launch control room, in the headsets of the controllers, in the sequencing computers that will manage the final automated seconds before ignition. But the pad is quiet, except for the hiss of the vent systems and the occasional sound of something mechanical adjusting to temperature. The rocket stands in the dark. The stars are above it, and somewhere in the mathematics of what happens next, the moment when the first stage engines ignite and the hold-down clamps release, and the structure begins its rise, that moment is already calculated, already planned, already as inevitable as anything built by human hands can be. The night is nearly over. The launch window is approaching. The pad waits. A rocket does not need anything to push against. This is the fact about rockets that most people have heard, and few have fully absorbed. The airplane pushes air backward with its propeller or its engine, and the air pushes back. the car pushes the road backward through its tires, and the road pushes back. The swimmer pushes the water backward with their arms and legs, and the water pushes back. Every form of transport you have ever used has worked by pushing against an external medium and receiving an equal and opposite push in return. A rocket in space has no external medium. There is no air, there is no road, there is nothing to push against, and yet it accelerates. It accelerates because it carries its own reaction mass with it. The fuel and the oxidizer in the tanks are the thing the rocket pushes against. It expels them at high velocity out of the nozzle at the rear, and the equal and opposite reaction to expelling that mass propels the rocket forward. Newton's third law does not specify that the thing you push against must be external to you. It only specifies that every action has an equal and opposite reaction. Expelling mass in one direction produces an equal and opposite force in the other direction. In space, with no air to provide resistance, the expelled mass travels away from the rocket freely and at maximum velocity, and the rocket is pushed with correspondingly maximum efficiency. This is the counterintuitive fact. A rocket works better in a vacuum than in air. In air, the exhaust gases have to push through the atmosphere to get out of the nozzle, and the atmosphere pushes back, reducing the effective exhaust velocity. In a vacuum, the gases exit freely, at the full velocity that the thermodynamics of the combustion allow, and every kilogram of expelled mass contributes its full momentum to pushing the rocket in the opposite direction. The physics governing this is the conservation of momentum. A rocket at rest in space has a total momentum of 0. When the engine fires and exhaust gases are expelled backward at high velocity, those gases carry momentum in the backward direction. For the total momentum of the system, rocket plus all the gas it has expelled, to remain 0, the rocket must carry equal momentum in the forward direction. Momentum is mass multiplied by velocity. As fuel burns and the rocket's mass decreases, the same thrust produces increasingly higher acceleration. The rocket gets lighter as it burns, and the same force accelerating a lighter mass produces higher velocity. This is why rockets accelerate continuously and increasingly throughout their burn. The first seconds of a launch feel slow. The enormous mass of a fully fueled rocket is accelerated only gradually, even by the enormous thrust of its engines. But as the fuel burns and the mass falls, the acceleration builds. By the time the first stage engines cut off, the vehicle may be experiencing several times the acceleration it felt at liftoff, with only a fraction of its original mass remaining. The exhaust velocity determines the efficiency of the engine. The faster the exhaust gases leave the nozzle, the more forward momentum is generated per kilogram of propellant consumed. Chemical propellants can produce exhaust velocities of approximately 2,000 to 4,000 meters per second, depending on the propellant combination. This puts a fundamental limit on the performance of chemical rockets, a limit imposed by the energy content of the chemical reactions available, not by any limitation of engineering. The rocket expels mass. Mass is pushed backward. The rocket is pushed forward, in empty space, against nothing, perfectly. On March 16, 1926, 4 people stood in a snowy field in Auburn, Massachusetts, and watched a 10-foot rocket made of thin pipes rise 41 feet into the air, fly for 2.5 seconds, and crash into the ice and snow 56 meters away. No newspaper reported it. The local press was not interested. The 4 witnesses, Robert Goddard, who had designed and built the rocket, his wife Esther, who was operating the motion picture camera, and 2 colleagues from Clark University, made no speeches and gave no interviews. Goddard noted the event in his diary with characteristic understatement. March 16th, tried rocket with engine on end, burned 20 seconds, rose slowly until it cleared the frame, and then, at express train speed, curving over to the left and striking the ice and snow. The rocket he called Nell, named later and not at the time, was the first liquid-fueled rocket ever to fly. It burned gasoline and liquid oxygen. The combustion chamber and nozzle were at the top of the rocket, not the bottom. Goddard had placed them there, believing the rocket would hang from the engine like a pendulum and achieve natural stability. The design placed the fuel tanks below, connected to the engine above by long, thin tubes. It did not look like any rocket you have seen since. It looked like a piece of experimental plumbing. It was, nevertheless, a moment as significant as anything in the history of technology. Not for the flight itself. 41 feet and 2.5 seconds are modest numbers, but for what the flight proved was possible. The flight proved that a liquid-fueled rocket engine could generate enough thrust to lift its own weight and the weight of its propellant, that the engine could sustain combustion for long enough to be useful, and that the fundamental physics of liquid propellant rocketry was sound. Goddard had been working on rocketry since before 1909, when he wrote his first notes on liquid-fueled propulsion. He had proved in a laboratory that a rocket motor works in a vacuum, a fact disputed by some of his contemporaries, who believed incorrectly that a rocket needed air to push against. He had published a theoretical paper in 1920, outlining the possibility of reaching extreme altitudes with rockets. The New York Times had mocked him in an editorial. He's suggesting that his claim that a rocket could work in the vacuum of space betrayed a lack of understanding of basic physics. The editorial was wrong. NASA's press office corrected it formally on July 17, 1969, the day after Apollo 11 launched. Goddard spent the remainder of his career refining his rockets, working eventually from a facility in Roswell, New Mexico, funded by the Guggenheim Foundation, after Charles Lindbergh personally intervened on his behalf. His rockets grew in sophistication and capability. He developed gyroscopic guidance, thrust vectoring through movable vanes, turbopump systems, regenerative cooling. He anticipated, largely in isolation, nearly every major feature of the rockets that followed. He died in 1945. He did not live to see the V2, or Sputnik, or the Saturn V, or any of the technologies that descended directly from his work. But on March 16, 1926, in a field in Auburn, Massachusetts, a woman filmed her husband's rocket rising into the winter sky. And everything that has ever been launched since was built on that. Inside a liquid rocket engine, something burns that should not be possible to contain. The combustion temperature in a liquid rocket engine, the temperature at which the propellant reacts inside the combustion chamber, ranges from approximately 3,000 to 3,600 degrees Celsius for the most common propellant combinations. Liquid hydrogen burning with liquid oxygen reaches the higher end of this range. Kerosene burning with liquid oxygen produces temperatures somewhat lower, but still far beyond anything that most engineering materials can survive. The nickel alloys and stainless steels that form the walls of the combustion chamber have melting points well below the temperatures the combustion reaches. By any straightforward analysis, the engine should destroy itself the moment it fires. It does not destroy itself because of regenerative cooling, a technique first developed and patented by Robert Goddard in the 1920s and used in virtually every high-performance liquid rocket engine since. In regenerative cooling, one of the propellants, typically the fuel, is routed through a network of small channels or tubes that run through the walls of the combustion chamber and the nozzle before being injected into the combustion chamber to burn. The fuel, arriving from the tank at cryogenic temperature, absorbs heat from the chamber wall as it flows through the cooling channels, at keeping the wall temperature below the material's melting point. By the time the fuel reaches the injector and enters the combustion chamber, it has warmed considerably, and the heat it absorbed from the wall is not lost. It becomes part of the energy available for combustion. The propellants are delivered to the combustion chamber by turbopumps, high-speed centrifugal pumps driven by turbines that run on hot gas tapped from the engine's own combustion. The pressures involved are extraordinary. The SpaceX Merlin engine that powers the Falcon 9 first stage delivers propellant to the combustion chamber at over 100 atmospheres of pressure. The turbopumps that generate this pressure spin at tens of thousands of revolutions per minute, handling cryogenic liquids at one end and hot combustion gases at the other, at power densities that exceed those of any other machinery in common use. The injector, the component that sprays the fuel and oxidizer into the combustion chamber in the pattern that ensures complete and stable combustion, is one of the most critical pieces of engineering in a rocket engine. Combustion instability, the tendency of the burning propellant to couple with the acoustic resonances of the chamber and generate self-amplifying pressure oscillations, can destroy an engine in fractions of a second. The history of rocket engine development is substantially a history of combustion instability problems encountered and solved, each solution adding another hard-won piece of knowledge to the accumulated engineering understanding of what makes an engine stable, if the combustion in the chamber is sustained at temperatures no material can directly withstand. The chamber wall is kept cool by the fuel it is about to burn. The engine fires continuously. The heat that would destroy it sustains it instead. The engineering that made this possible took decades to develop, was worked out largely in secret, is invisible in operation, and makes everything above it possible. The fire burns, the wall stays cool, the rocket rises. The nozzle is the shape that made the space age possible. Not the engine, not the propellant. The nozzle, specifically the convergent-divergent nozzle design, derived from the work of the Swedish engineer Carl de Laval in the 1880s and first applied to a rocket engine by Robert Goddard in 1926. The de Laval nozzle is what takes the chaotic, high-temperature, or high-pressure combustion products in the chamber and converts them into a directed, organized, supersonic jet. Without it, a rocket engine produces a fraction of its potential thrust. With it, the efficiency increases dramatically. Goddard's application of the nozzle to his solid fuel engine doubled its thrust and raised its efficiency from approximately 2% to 64%. The nozzle works by exploiting the counterintuitive aerodynamics of compressible flow. In subsonic flow, a narrowing passage accelerates the gas. This is familiar from the behavior of water in a garden hose, where pinching the end increases the velocity of the stream. But gas flowing at supersonic speed behaves the opposite way. In a narrowing passage, a supersonic flow decelerates. A diverging passage, one that widens, accelerates it further. The Laval nozzle combines these two behaviors in sequence. The nozzle first converges, narrows toward a minimum area called the throat. The hot combustion gases accelerate as they approach the throat, reaching exactly the speed of sound at the throat itself. Then the nozzle diverges, widens progressively from the throat to the exit. In this diverging section, the now supersonic flow continues to accelerate, the gas expanding and cooling as it converts its thermal energy into directed kinetic energy. By the time the exhaust leaves the nozzle exit, it is moving at 2,000 to 4,000 meters per second, depending on the propellant combination. A directed supersonic jet carrying the momentum that propels the rocket. The shape of the diverging section matters. The expansion ratio, the ratio of the nozzle exit area to the throat area, determines how much the gas expands, and consequently, how much of the thermal energy is converted to kinetic energy. A larger expansion ratio extracts more energy, but produces a larger, heavier nozzle. The optimum expansion ratio depends on the ambient pressure. A nozzle optimized for sea level operation is not optimized for vacuum, and vice versa. The Saturn V's first stage engines had relatively modest expansion ratios designed for the lower atmosphere. The upper stage engines, operating in near vacuum, had larger, more expanded nozzles. The nozzle also provides the direction. The hot combustion products in the chamber exert pressure equally in all directions, and the nozzle directs the exhaust in one direction only, backward, converting omnidirectional pressure into unidirectional thrust. The shape of the nozzle is also the structure that must contain the forces of this process. The materials and thicknesses calculated to survive the pressures and temperatures of operation for the duration of the engine burn. The nozzle is visible from the ground as the engine bell, the flared, glowing structure at the base of each engine, visible in any launch photograph as the source of the fire and the smoke. What the photograph shows is the product of extraordinary invisible engineering. Gas at over 3,000 degrees Celsius, expanded through a precisely calculated geometry, departing at supersonic speed in a column of directed thrust. The shape does the work. The rest is fire and mathematics. The problem with a rocket is that it must carry everything, not just the payload, the satellite, the spacecraft, the crew, not just the fuel, the oxidizer too, because there is no oxygen in space and the fuel cannot burn without it, and the tanks to hold the fuel and the oxidizer, and the engines, and the structure that holds all of this together against the aerodynamic forces of ascent and the acceleration, loads of the engine firing. Everything the rocket needs to perform its mission. The rocket must carry with it from the moment it leaves the pad. This is a compounding problem, and its severity was understood mathematically before the first rockets were ever built. The Tsiolkovsky rocket equation, derived by the Russian schoolteacher Konstantin Tsiolkovsky in 1903, independently derived by Goddard and others later, relates the change in velocity a rocket can achieve to its exhaust velocity and its mass ratio. The mass ratio is the ratio of the rocket's mass at the beginning of the burn to its mass at the end, after the fuel is consumed. The relationship is exponential and unforgiving. To achieve a high velocity change, you need a very large mass ratio, meaning the fuel must be a very large fraction of the vehicle's total mass. To reach low Earth orbit from the ground requires a velocity change of approximately 9 to 10 kilometers per second. At typical chemical propellant exhaust velocities of around 3 to 4 kilometers per second. Achieving this with a single-stage vehicle would require the propellant to be approximately 90% or more of the total mass at launch, leaving almost nothing for structure, engines, payload. In practice, the structural and engine mass required makes a single-stage to orbit vehicle with chemical propellants extraordinarily difficult and inefficient. The solution is staging. Break the rocket into sections and shed each section as its propellant is exhausted. The first stage carries the second stage carries the third, and so on. When the first stage exhausts its propellant and its engines cut off, it is jettisoned. The empty tanks and the engines, now dead weight, are discarded. The second stage ignites, and now its mass ratio calculation benefits from starting with a much lighter vehicle. The first stage's mass is simply gone. Staging allows each portion of the rocket to be optimized for its specific phase of flight. The first stage operates in the dense lower atmosphere, where aerodynamic forces are high, and the engines are optimized for sea level operation. The upper stages operate in near vacuum, where the nozzles can be designed with larger expansion ratios for higher efficiency. The Saturn V's 3 stages each covered a different portion of the energy budget required to reach the Moon. The first providing the bulk of the energy to escape the lower atmosphere, the second completing the journey to orbit, the third providing the push toward the Moon. The Saturn V's first stage, the SIC, burned for approximately 161 seconds. In that time, it consumed 2.5 million kilograms of propellant and raised the vehicle to an altitude of roughly 68 kilometers and a speed of approximately 9,900 kilometers per hour. Then, its engines cut off and it separated. 8 retro rockets on the first stage fired briefly to slow it relative to the ascending vehicle above, preventing it from bumping into the second stage. The first stage fell away into the Atlantic Ocean, its job complete, never to be used again. The vehicle it left behind, the second and third stages, and the Apollo spacecraft weighed a fraction of what had lifted off. Lighter, faster, still climbing. The next engine already igniting. The ocean below already far away. The Saturn V was 111 meters tall. This number does not produce the right image without context. The Statue of Liberty, so from ground to torch, is approximately 93 meters. The Saturn V was 18 meters taller than the Statue of Liberty. And the Statue of Liberty is not a small object, a 36-story building. That is the Saturn V standing on its launch pad, before any of it moves, before any engine fires, before any of its 2.8 million kilograms of mass does anything except press against the launch structure under its own weight. It weighed 2.8 million kilograms fully fueled. This is approximately the weight of 400 elephants, or 450 million standard paperclips, or, to use a comparison that may be more viscerally useful, roughly the weight of the Eiffel Tower, one of the heaviest large structures in the world, multiplied by 3. All of this sitting on the pad, held down by 4 enormous hold-down arms that would release at the moment of launch confirmation. The thrust at liftoff was 34.5 million newtons, equivalent NASA noted, to the power output of 85 Hoover dams simultaneously. All of this produced by 5 Rocketdyne F1 engines arranged in a quincunx at the base of the first stage, 1 at the center and 4 at the corners, the 4 outer engines capable of being gimbaled hydraulically to steer the vehicle. Each F1 engine alone produced more thrust than any complete rocket built before the Saturn V program began. The first stage burned for approximately 161 seconds, not quite 3 minutes. In those 3 minutes, it consumed 770,000 litres of kerosene fuel and 1.2 million litres of liquid oxygen, delivering the vehicle to an altitude of roughly 68 kilometres at a speed of approximately 9,900 kilometres per hour. Then, the first stage separated, and the second stage's 5 J2 engines ignited, each burning liquid hydrogen and liquid oxygen, continuing the climb toward orbit. The second stage burned for approximately 395 seconds. Then it too separated. The third stage's single J2 engine completed the job of reaching Earth orbit. 13 Saturn V rockets were launched between 1967 and 1973. 12 of them carried Apollo missions. The 13th launched the Skylab space station. All 13 succeeded in their primary mission. Of the 12 Apollo missions, 6 landed astronauts on the Moon. None of the Saturn V launches failed. The rocket was designed by a team at NASA's Marshall Space Flight Center, led by Wernher von Braun, says drawing on the engineering knowledge accumulated across 2 decades of American, and, before that, German rocket development. It was manufactured by Boeing for the first stage, North American Aviation for the second, Douglas Aircraft for the third, and assembled in the Vehicle Assembly Building at Kennedy Space Center. Itself one of the largest structures ever built. Its interior volume large enough that clouds sometimes form below its ceiling. The last Saturn V launched on May 14, 1973. No rocket of comparable capability has been launched since. The record for the most powerful rocket ever flown, set in 1967, has not been broken, and the Saturn V itself, the vehicle that carried human beings to the surface of another world, stands today in several pieces in museums in Texas and Florida and Alabama, and the last examples of a machine that existed for 6 years and accomplished things that are not yet fully replicated. 111 meters, 36 stories, still the largest thing that ever flew. The hold-down arms release, and for a moment, nothing seems to happen. The 5 F1 engines of the Saturn V first stage were ignited approximately 8 seconds before the scheduled liftoff, not at the moment of liftoff. The ignition sequence was staggered. The engines came up to full thrust in sequence over those 8 seconds. The entire vehicle held against the pad by the hold-down arms, while the engine performance was confirmed by the automated sequencing system. Only when all 5 engines were confirmed at full thrust, only when the measured performance met the required parameters, did the hold-down arms release. And, for what appeared from the ground to be a long, slow moment, the Saturn V simply sat there with its engines running. The delay was not mechanical hesitation. It was physics. The thrust required to lift 2.8 million kilograms off the ground was 34.5 million newtons, exactly enough to overcome gravity at launch mass. The rocket did not leap from the pad. It rose at the rate that physics dictated, very slowly at first, the thrust barely exceeding the weight. the vehicle gaining speed by centimeters per second in the first moment, then meters per second, the acceleration building as the propellant burned and the mass fell. The launch tower clearance. The moment the vehicle's bottom cleared the top of the launch structure took several seconds. A fully fueled Saturn V was essentially weightless in thrust terms at the moment of liftoff, so the trajectory after liftoff was not straight up. The vehicle began a pitch and roll maneuver almost immediately after clearing the tower, rotating to align its trajectory with the planned orbital inclination. A precise combination of pitch, roll, and yaw that placed the vehicle on the exact flight path calculated weeks before by the trajectory analysts. From the ground, a Saturn V launch appears to arc over the horizon almost immediately. The roll maneuver is visible even in photographs taken seconds after liftoff. Approximately 80 seconds after liftoff, the vehicle reached the condition called max Q, maximum dynamic pressure. This is the point of highest aerodynamic stress on the vehicle, the product of atmospheric density, which is decreasing as altitude increases, and the square of velocity, which is increasing as the engines accelerate the vehicle. Max Q represents the peak of the aerodynamic load that the structure must withstand, the moment at which the combination of speed and air density places the greatest bending and compressive force on the vehicle's thin metal skin. The engines were typically throttled back slightly to reduce thrust at this point, keeping the aerodynamic loads within structural limits. After max Q, as the air continued to thin faster than the velocity increased, the aerodynamic stress fell, the engines returned to full thrust, and the vehicle continued to accelerate. At approximately 135 seconds after launch, the center F1 engine was shut down to limit the acceleration as the vehicle grew lighter. 15 seconds later, at T plus 161 seconds, the 4 remaining F1 engines shut down simultaneously. In those 161 seconds, the vehicle had risen to approximately 68 kilometers. The first stage separated, the second stage ignited. The most powerful engines ever to fly were already falling away behind it. The sky above was already dark. The vehicle was accelerating into it. The atmosphere is thinner than almost anyone imagines. If the Earth were reduced to the size of a standard classroom globe, approximately 30 centimeters in diameter, the atmosphere at that scale would be thinner than the coat of varnish on the globe's surface. The air that sustains every living thing on the planet, that drives the weather and scatters the light that makes the sky blue, occupies a shell around the Earth so thin, relative to the planet's size, that from orbit it is visible as a pale blue line against the black of space. A line that seems, to anyone who has seen photographs taken from orbit, disturbingly fragile. A rocket ascending from the launch pad reaches the internationally recognized boundary of space, the Kármán line, at 100 kilometers altitude, in less than 10 minutes. Not because it is moving slowly, but because that boundary, though it seems impossibly high from the ground, is genuinely close to the surface in the context of the distances involved in spaceflight. Low Earth orbit begins at roughly 200 kilometers altitude. The Moon is 384,000 kilometers away. The atmosphere that must be crossed to reach orbit is, in those terms, the thinnest of membranes. The experience of ascending through the atmosphere in a rocket is one of progressive transition, rather than a single crossing. At sea level, the air is dense enough that aerodynamic forces dominate. The vehicle must be shaped to minimize drag. The engines must overcome both gravity and atmospheric resistance. The structure must withstand the aerodynamic loads. At max Q, around 80 seconds into the flight and approximately 12 kilometers altitude, the aerodynamic stress peaks, and the vehicle is at its most vulnerable to structural failure from wind shear or gusts. Above this point, the air thins rapidly, the pressure falling exponentially with altitude, and the aerodynamic forces diminish faster than the velocity increases. At around 50 kilometers altitude, the air is thin enough that aerodynamic control surfaces cease to be useful. Fins and control vanes cannot generate meaningful forces in air this thin. The vehicle is steered instead by gimballing the engines, pointing their thrust slightly off-center to rotate the vehicle around its center of mass. At 80 kilometers, the sky above the vehicle is visibly black. The scattering of sunlight that produces the blue sky requires enough air density that above this altitude, the sky is no longer blue in the upward direction. The stars are visible in daylight. At 100 kilometers, the air is so thin that an aircraft wing would need to move at orbital velocity to generate the lift required to support its own weight, at which point it is, by definition, in orbit rather than flying aerodynamically. This is the Kármán line, not an arbitrary designation, but a physically meaningful boundary where aeronautics ends and astronautics begins. Above it, only rocket thrust can maintain altitude. On the fairing, the aerodynamic nose cone that protects the payload from the aerodynamic heating of the ascent through the lower atmosphere is jettisoned at altitude, typically around 100 to 120 kilometers, when the dynamic pressure has fallen to a level at which heating is no longer a concern. After fairing separation, the payload is exposed to space for the first time. The blue line below, the black above, the rocket still climbing, the atmosphere already behind it, not below it, thinner from here than anyone on the ground believes. Orbit is not a place above the Earth. It is a way of falling around it. The distinction matters because it changes what orbit feels like and what it means. An object in orbit is not sitting still above the planet, held up by some force. It is falling continuously towards the Earth's surface. What prevents it from hitting that surface is not the absence of gravity, but the fact that it is moving fast enough horizontally that the Earth's surface curves away beneath it as fast as it falls toward it. The object falls, the surface falls away, and the distance between them stays constant. It is perpetual falling with perpetual missing. The velocity required to maintain this condition in low Earth orbit, where the atmosphere is thin enough to neglect but gravity is still close to its full surface value, is approximately 7.8 kilometers per second. This is not the speed of sound, which is about 0.34 kilometers per second. It is not the speed of a commercial aircraft, which is approximately 0.25 kilometers per second. It is 23 times the speed of sound. At this velocity, a single circuit of the Earth takes approximately 90 minutes. An object in low Earth orbit experiences 16 sunrises and 16 sunsets every 24 hours. The counterintuitive relationships of orbital mechanics follow from this basic physics. To go faster in orbit, you burn your engine in the direction of travel. This raises your altitude. A higher orbit has a lower velocity. You are moving faster in the sense of having more total energy, but the orbital speed at the higher altitude is actually lower than at the original altitude. To slow down, to re-enter, or to lower your orbit, you burn your engine against the direction of travel. This reduces your energy, drops your perigee, and allows the atmosphere to slow you further. You go from moving at 7.8 kilometers per second to slowing, heating, and descending over the course of a re-entry that may last 40 minutes or more. Reaching orbit from the ground requires not just reaching 100 kilometers altitude, but reaching that altitude while moving at approximately 7.8 kilometers per second horizontally. The altitude part is relatively easy. A modest-sounding rocket can reach 100 kilometers. The velocity part is the hard part. The enormous energy required to accelerate to 7.8 kilometers per second is why orbital launch vehicles are so large and so complex, and why a Saturn V, a machine 36 stories tall, was required to send 3 people to the moon. The orbit itself, once achieved, is perpetually stable in the absence of atmospheric drag. At true orbital altitude, above the discernible atmosphere, an object in orbit stays in orbit indefinitely with no engine thrust. The International Space Station requires periodic reboost to counteract the tiny but non-zero atmospheric drag at its altitude of approximately 400 kilometers. Without it, the station would gradually lose altitude and re-enter within years. Below orbital altitude, the atmospheric drag is more significant and the timescale shorter. The rocket's job is to achieve the orbit. Once the orbit is achieved, the rocket's job is done. Physics takes over. The falling continues. And from 400 kilometers above the surface, the Earth turns slowly below, day and night, cycling every 90 minutes. The thin blue line of atmosphere at the edge of the horizon, the black of space above it, still and completely silent. In 1903, a schoolteacher in the small Russian town of Kaluga sat down and derived the equation that governs all rocketry. Konstantin Tsiolkovsky was not a university professor. He had no laboratory. He had no colleagues working on the same problems. He had been deaf since the age of 9, which had prevented him from attending a conventional school, and had driven him instead to self-education in the public libraries of Moscow, where as a young man he had read voraciously and taught himself mathematics and physics from first principles. He had moved to Kaluga to teach mathematics at a local school, and he spent his evenings working on the theoretical problems of space travel in the wooden house, where he lived without running water. He published his rocket equation in 1903 in a paper titled The Exploration of Cosmic Space by Means of Reaction Devices. The paper was not widely read. It appeared in a Russian science journal with a limited circulation, in a language that few of the Western scientists who would have been most interested in it could read. Tsiolkovsky's priority in deriving the equation was not widely acknowledged until decades later, when the space age had already begun and the historical record was being reconstructed. The equation he derived is simple to write and profound in its implications. It states that the change in velocity a rocket can achieve is equal to the exhaust velocity of its engine, multiplied by the natural logarithm of the ratio of the rocket's initial mass to its final mass, the mass ratio after the fuel has burned. The natural logarithm is what makes the equation demanding. It means that to double the achievable velocity change, you do not double the fuel load, you square the mass ratio. To achieve each additional increment of velocity, you must carry exponentially more propellant for each kilogram of payload. Tsiolkovsky derived this equation from Newton's laws and from the basic principles of momentum conservation. The derivation is not, in retrospect, technically difficult. Anyone with a solid grounding in calculus and physics could follow it. What was remarkable was that Tsiolkovsky recognized the problem it was addressing. In 1903, there were no liquid-fueled rockets. The Wright brothers had not yet flown at Kitty Hawk. The concept of a rocket that could reach space was a fantasy in popular literature, not a subject of serious scientific investigation. Tsiolkovsky was solving a problem that almost nobody else had yet identified as a real engineering challenge. He was also, by all accounts, thoroughly aware of what his equation implied, when the mass ratios required to reach orbit were so large that a single-stage chemical rocket seemed nearly impossible. He proposed multi-stage rockets, the concept that would make orbital flight achievable, and he understood that liquid propellants would be necessary, offering higher exhaust velocities than the gunpowder rockets that were the only rockets his contemporaries had access to. He did not build a rocket. He did not have the resources or the engineering support. He thought and wrote and derived and proposed. The wooden house in Kaluga, no running water, the equation that governs every rocket ever launched, written out on paper, in the margins of the space age. Before the space age existed, some rockets cannot be stopped once they are started. A solid rocket motor, the other main category of rocket propulsion, and distinct from the liquid-fueled engines in the Saturn V and the Falcon 9, carries its fuel and oxidizer pre-mixed in a solid form called grain, cast directly into the motor casing, which serves as both propellant container and combustion chamber. When the igniter fires, the grain begins to burn from its inner surface outward, producing hot combustion gas that exits through the nozzle. There is no pump, no turbo machinery, no separate propellant tanks, no complex plumbing. The motor is, in essence, an extremely precisely engineered large firework. And like a firework, once it is lit, it burns until the propellant is consumed. There is no throttle. There is no off switch. The burn rate of the grain is determined by its chemistry and its geometry, the shape of the central channel, the composition of the propellant, and these are fixed at manufacture. A solid rocket motor that begins its burn will finish its burn on whatever schedule the grain design dictates, regardless of what is happening around it. This is simultaneously the solid rocket's greatest limitation, and one of the reasons it has been used so extensively. The inability to throttle or shut down is a significant disadvantage in applications where mission flexibility is required. But the simplicity that comes from having no turbopumps, no cryogenic propellants, no complex feed systems, no ignition sequence that must be precisely managed, that simplicity means that a solid rocket motor can be stored for decades in a ready-to-fire condition and ignited with a single electrical command. And this is why the world's nuclear-armed ballistic missiles, the Minuteman III, the Trident II, use solid propellants. They must be ready to launch at any moment, storable indefinitely, reliable absolutely. The Space Shuttle's solid rocket boosters, the two white cylinders attached to the sides of the external tank, each stood 45.5 meters tall and produced approximately 12.5 million newtons of thrust at liftoff. Together, they provided approximately 70% of the shuttle's total liftoff thrust, the the 3 main engines on the orbiter providing the remaining 30. The boosters burned for approximately 124 seconds before separating at an altitude of 45 kilometers and descending by parachute to the Atlantic Ocean, where recovery ships retrieved them for refurbishment and reuse, a partial solution to the economics of solid rocket disposal. The solid rocket's history stretches back to the earliest fireworks. Chinese military forces were using solid propellant rockets in the early 13th century. The British military engineer William Congreve developed solid rockets used in warfare in the early 19th century. The rockets visible in the Battle of Baltimore in 1814, the event that put the phrase "the rocket's red glare" into the American national anthem. Every bottle rocket and every emergency signal flare and every sounding rocket launched to study the upper atmosphere is a direct descendant of this line of development. The simplest version of the technology that reaches space. No moving parts, no pumps, no cryogenics, a shaped cylinder of propellant, an igniter, and the fire that cannot be stopped until it has burned itself out. The Earth from low orbit does not look the way it looks in photographs. Photographs compress it, flatten it, reduce it to something displayable on a screen or printable on a page. The experience described by astronauts and cosmonauts, many of whom have struggled to find language adequate to it, is of something qualitatively different. The scale of the planet, the physical immediacy of the curvature, the impossible vividness of the colors, the disorienting clarity of the view. The curvature is the first surprise. From the surface, the Earth appears flat. The horizon is far enough away that the arc is imperceptible, and the brain processes the visual field as a plane. From 400 kilometers altitude, and the curvature is unmistakable. The horizon is a curve, the visible disk of the Earth below, subtending an angle large enough that the sphere is apparent in a single glance. The planet is present as a sphere in a way that no photograph has quite managed to communicate, because the photograph removes the peripheral vision and the sense of orientation that make the curved horizon comprehensible. The colors are the second surprise. The ocean is a blue that has no precise terrestrial equivalent, described variously as electric, as luminous, as deeper and more saturated than any sky or any sea surface seen from the ground. The shallow water around atolls and continental shelves shows in turquoise and pale green, the different depths readable as different colors in a map-like clarity. The Sahara is a precise shade of ochre and orange. The Amazon basin is a dark, dense green that absorbs light rather than reflecting it. The ice caps are white with a blue tinge. The cloud systems are brilliant white, three-dimensional, their shadows visible on the ocean surface below them. The atmosphere, seen from above, is the thin blue line at the limb of the Earth, the edge of the planet as seen from orbit. This line, perhaps 10 to 15 kilometers thick in the lower density layers that matter most for life, is what separates the surface from the void. From the ground it is invisible, too close to see as a layer. From orbit it is visible, and it is visibly thin. Astronauts who have described it report that the fragility of the atmosphere is one of the most visceral impressions of orbital flight. Not an abstract concern about climate, but a direct visual perception that the film of air supporting all life on the planet is a very thin film. 16 times per day, the day-night terminator, the moving line of sunrise and sunset, sweeps across the surface below the orbiting station. Each terminator crossing takes minutes. The station crosses from full daylight to full darkness in the time it takes to walk from one end of the station to the other. In the moments of terminator crossing, the thin atmosphere refracts the sunlight into colours not visible from the surface. Deep reds and oranges in the limb, the shadow of the Earth projected into space as a dark wedge, at the upper layers of the atmosphere glowing in colours that have been described as unlike anything seen from the ground. The aurora from above is not a curtain seen from the side. It is a river of light seen from above, a luminous green and white swirl that moves across the polar regions below the orbiting station. The charged particles of the solar wind spiraling into the magnetic field lines and releasing their energy as light in the upper atmosphere. All of it visible from above, in a geometry that the ground-based observer never sees. The station passes overhead. The planet turns below. 16 sunrises, every day, without exception. Coming home is harder than leaving. A spacecraft returning from orbit carries an enormous amount of kinetic energy, the energy of moving at 7.8 kilometers per second. This energy does not disappear. It cannot be simply switched off. It must go somewhere, and in a re-entry from low Earth orbit, it goes into heat. The spacecraft's kinetic energy is converted, through the friction of the atmosphere, into thermal energy. Temperatures on the heat shield surface reaching approximately 1,650 degrees Celsius for a typical capsule returning from low Earth orbit, and over 2,700 degrees Celsius for a vehicle returning from the Moon. The plasma sheath is the visible consequence of this heating. At re-entry speeds, the air in front of the spacecraft cannot get out of the way fast enough to flow around it smoothly. Instead, the air is compressed so violently, in fractions of a millimeter of the bow shock in front of the heat shield, that it heats to plasma temperatures, the electrons stripped from their atoms, the gas glowing, and the spacecraft descends inside a sheath of hot plasma that is itself the product of the spacecraft's own momentum being converted to heat. This plasma sheath blocks radio communication. During the communications blackout, typically lasting several minutes for a capsule returning from low Earth orbit, the spacecraft cannot receive signals from the ground and cannot transmit. The flight controllers on the ground, who have monitored every second of the mission in real time, must wait in silence for the blackout to end and the spacecraft to re-establish contact. The communication blackout is one of the most tense intervals in any mission with a crew aboard. The controllers know the spacecraft should be surviving the re-entry, but they cannot know it for certain until the signal returns. The heat shield material absorbs and dissipates the thermal energy by ablating. The outer surface of the shield is deliberately designed to char and erode away. The vaporization of the ablative material carrying heat away from the surface rather than conducting it through to the spacecraft interior. The Apollo command module's heat shield was made of a material called Avcoat, an epoxy novolac resin in a fiberglass honeycomb, approximately 70 millimeters thick at the center where the heating was greatest. The space shuttle's ceramic tiles served the same purpose, but were designed to be non-ablating and reusable. Each tile inspected, repaired, and reinstalled between flights. SpaceX's Dragon capsule uses a Pica X ablative material derived from earlier NASA research, updated for the specific re-entry conditions of commercial crew missions. The angle of the re-entry trajectory is critical and unforgiving. Too steep, and the deceleration forces exceed what the spacecraft structure, and any crew aboard, can survive, and the heating rate overwhelms the heat shield. Too shallow, and the spacecraft skips off the upper atmosphere like a stone off water, bouncing back into a higher orbit or out of the Earth's gravitational influence entirely. The correct angle is a narrow corridor, a few degrees wide, that has been calculated precisely and must be hit precisely. The guidance computers maintain the re-entry trajectory throughout the descent. Below the plasma sheath, as the spacecraft decelerates through the lower atmosphere, the heat shield cools, the glow fades, the communication blackout ends. The signal returns. The flight controllers hear the voice they have been waiting for. The spacecraft has crossed back. The fire survived. The home side of the atmosphere below. The best rocket propellant, in terms of the performance it delivers, is also one of the most difficult substances to work with. Liquid hydrogen, the fuel used in the upper stages of the Saturn V, in the Space Shuttle main engines, in the Ariane 5 and Ariane 6 core stages, and in numerous other high-performance rockets, has the highest specific impulse of any chemical propellant when burned with liquid oxygen. Specific impulse, measured in seconds, is the standard figure of merit for rocket propellant efficiency. The higher the specific impulse, the more thrust is generated per kilogram of propellant consumed per second. Liquid hydrogen and liquid oxygen together achieve a specific impulse in vacuum of approximately 450 seconds, meaningfully higher than kerosene and liquid oxygen, which achieves around 350 seconds vacuum specific impulse. The performance advantage of liquid hydrogen is real and significant. It is why the upper stages of the Saturn V, the stages that had to complete the journey to orbit and then push the spacecraft toward the moon, used liquid hydrogen rather than the kerosene used in the more powerful but less efficient first stage. Efficiency matters more on the upper stages, where every kilogram of propellant saved directly reduces the payload cost. The difficulty of working with liquid hydrogen is also real and significant. Liquid hydrogen exists at -253 degrees Celsius, just 20 degrees above absolute zero, the coldest temperature theoretically possible. At this temperature, almost every material in the universe is a solid. Most metals become brittle. Seals and gaskets designed for normal temperatures fail. The pipes and valves and fittings that convey the hydrogen from its tank to the engine must be designed specifically for cryogenic service and must be tested extensively to ensure they maintain integrity at these temperatures under the pressures of flight. Liquid hydrogen is also extremely light, the lightest element, and in its liquid form still dramatically less dense than water. A tank holding a useful quantity of liquid hydrogen by mass is much larger than the equivalent tank for kerosene, because the same mass of liquid hydrogen occupies roughly 7 times the volume. This means larger tanks, heavier tank structures, and more aerodynamic drag, costs that partially offset the propellant performance advantage. Kerosene, specifically the highly refined, low-sulfur RP1 grade used in rocket engines, burns cooler, is denser, and is simpler to store and handle. It is liquid at room temperature. It does not boil off during fueling. It does not require cryogenic insulation. The SpaceX Falcon 9 uses RP1 and liquid oxygen, the Falcon 9's Merlin engines, burning approximately 250 kilograms of propellant per second per engine at full thrust, delivering a compromise between the simplicity of kerosene and the performance of the liquid oxygen oxidizer. The SpaceX Raptor engine, used in the Starship launch system, burns methane and liquid oxygen, a combination that offers performance between kerosene and hydrogen, with the methane's advantage of being potentially manufacturable on Mars from local resources, an option that has driven its selection for a vehicle explicitly designed with Mars missions in mind. The choice of propellant shapes the rocket. The rocket's shape determines what it can carry. What it can carry determines what humanity can reach. Every trade-off, from the density of kerosene to the boiling point of hydrogen, ultimately expressed in the missions the rocket can or cannot fly. The F-1 engine almost killed the Apollo program. Not through failure in flight. The F-1 flew flawlessly on every Saturn V mission. The problem came during development, years before the first launch, when the engineers building the engine encountered a phenomenon they could not control and did not fully understand. Combustion instability, the tendency of the burning propellant mixture inside the combustion chamber to couple with the acoustic resonances of the chamber and produce violent, self-amplifying pressure oscillations, was destroying test engines within fractions of a second of ignition. The pressure pulses were so severe and so rapid that they shredded the injector face and fractured the combustion chamber before any human response was possible. The F-1 produced 6.7 million newtons of thrust from a single combustion chamber, the highest thrust of any single-chamber liquid rocket engine ever built and flown. To generate this thrust, it burned 1,789 kilograms of propellant per second, roughly 800 kilograms of liquid oxygen, and 989 kilograms of RP-1 kerosene, injected through a precisely patterned injector face into the combustion chamber and ignited into a sustained, controlled burn at approximately 3,300 degrees Celsius. The chamber pressure was 70 atmospheres. At these scales, the slightest asymmetry in the combustion, the slightest tendency for the burning to become uneven, could initiate an acoustic oscillation that the combustion itself would then amplify. The Rocketdyne engineers working on the F-1 in the late 1950s and early 1960s solved the combustion instability problem not through theoretical derivation, but through exhaustive empirical testing. They modified the injector geometry in thousands of small variations, testing each configuration, observing which ones were stable and which were unstable, and building up an empirical map of injector designs and their stability characteristics. They developed a technique of deliberately bombing the combustion chamber, igniting small explosive charges inside the running engine to introduce artificial disturbances, and measuring how quickly the combustion damped out the disturbance and returned to stable operation. An engine that could recover from a bomb test in 20 milliseconds was considered stable. One that could not was redesigned. By the time the F-1 reached its final production configuration, the combustion instability problem had been solved through this process of systematic empirical investigation. The solution was built into the injector design. The specific geometry of the fuel and oxidizer ports, the baffles positioned across the injector face to interrupt the acoustic modes that would otherwise amplify. The solution worked. Not one F-1 engine suffered combustion instability in flight. 5 of them burned on every Saturn V first stage. Together, they produced 33.4 million newtons of thrust. Together, they burned for 161 seconds, the most powerful propulsion system ever to carry human beings away from the Earth. Built on thousands of test firings, hundreds of modified injectors, and the patient, iterative, unspectacular engineering discipline of solving one problem at a time until all of them were solved. The launch control room is quiet in the way that a surgery is quiet, not silent. There are voices, measured and precise, calling out data and confirmations and status reports in a continuous low stream. And the system's controllers sit at their consoles in rows facing the large displays at the front of the room, each one responsible for a specific set of vehicle parameters. The propulsion officer monitoring engine performance, the guidance officer tracking the navigation system, the flight dynamics officer watching the trajectory, the range safety officer with authority to terminate the flight if it deviates from its planned corridor in a way that threatens populated areas. The launch director sits at a raised console at the back, overseeing the entire operation, the final human authority before the automated launch sequence takes over. The discipline that governs this room was learned over decades, across every launch and every anomaly investigation and every accident review. The culture of launch operations is a culture of checklists, or of verification, of the specific discipline of not proceeding past a checkpoint until the checkpoint has been confirmed clear. Each step in the countdown is gated by confirmations from the systems responsible for that step. The launch director does not proceed from T minus 10 minutes to T minus 5 minutes until every controller has confirmed their system ready. The culture was built on the experience of what happens when that discipline is relaxed. The final minutes of a countdown have a character distinct from all other human activities. In the room, each of the controllers has been working through their portion of the checklist for hours before the final countdown began. At the launch window, the period during which the launch can occur and still place the vehicle in the correct orbit, may be seconds wide or minutes wide depending on the mission. Outside the window, the physics of orbital mechanics are unforgiving. Launch a minute late and the launch site has rotated to the wrong position. The vehicle would need to fly a different trajectory. The propellant budget would not close. The countdown has no flexibility at the end. At T minus 33 seconds on a Saturn V launch, the automated launch sequencer took over from the manual countdown. The last 33 seconds were controlled by computers, the sequencer running through the final steps at the rate the physics demanded. The engine ignition sequence, the hold down arm release, or the liftoff confirm, faster than human reaction time could have managed. The flight controllers watched, the consoles showed, the displays updated, and at the moment of ignition, in a room several kilometers from the pad, the room filled with the light of the flame before the sound arrived. Light travels at 300,000 kilometers per second, sound at 343 meters per second, and at a distance of several kilometers, the delay is perceptible. The controllers saw the rocket rise in silence for several seconds before the sound reached the building and the walls began to vibrate. The room watched the vehicle climb. The data streams continued. The controllers called their system statuses. Normal, 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 and the rocket went where it was sent. The first stage of the Falcon 9 lands itself, not metaphorically, physically, autonomously, propulsively. After separating from the second stage and the payload at approximately 70 kilometers altitude, the first stage performs a series of maneuvers. It reorients to fly engine end forward. It fires its engines to slow its downrange velocity and bring its trajectory back toward the launch site, or toward the drone ship, a modified barge, autonomously positioned at sea. Its name either, "Of course, I still love you," or a shortfall of gravitas, depending on which ocean it operates in. It deploys grid fins, small, lattice structure aerodynamic control surfaces that extend from the top of the stage and steer it through the atmosphere during the final descent. And, at an altitude of approximately 3 kilometers, it fires its engines for the landing burn, a precisely calibrated deceleration that slows the stage from several hundred meters per second to nearly zero in the seconds before touchdown. The legs deploying from the base of the stage as it descends the final meters. The legs touch the pad, the engines cut off, the stage stands vertical on the landing pad or on the drone ship deck. SpaceX flew the first successful Falcon 9 first stage recovery on December 21st, 2015. By April 2026, they had completed well over 200 successful first stage recoveries. The same first stage boosters have been reflown as many as 20 times or more. The economics of this reuse are significant. A new Falcon 9 first stage costs tens of millions of dollars. The propellant and refurbishment cost of reflying a recovered stage is a fraction of that. Reusability was the hypothesis that SpaceX was founded to test, and the landing footage, still surprising, still visually arresting, even after hundreds of repetitions, confirmed it. The broader landscape of current launch vehicles reflects a generation of development that the Saturn V era made possible in principle, and that private investment and competitive pressure have made practical. The United Launch Alliance Vulcan, using BE-4 engines developed by Blue Origin, represents the evolution of the American expendable launch vehicle tradition toward more capable and cost-competitive systems. The European Ariane 6, launched from French Guiana, continues the tradition of European independent access to space that the Ariane 5 established. The Japanese H-3, after its initial development difficulties, has entered service as Japan's next-generation medium to heavy lift vehicle. SpaceX's Starship, the fully reusable two-stage to orbit system using the Super Heavy booster and the Starship upper stage, both intended to land and be reflown, is in active flight testing as of early 2026, with both stages having demonstrated successful return and landing in test flights. The system, if its reusability goals are achieved, would represent the most significant reduction in the cost per kilogram to orbit in the history of spaceflight. The rockets flying now are not the same rockets as the Saturn V. They are not as tall. They do not carry as much. They do not send human beings to the moon, but they launch more frequently than the Saturn V ever did. They carry more mass to orbit per year than any previous generation, and some of them land themselves, autonomously, on a barge in the sea, still standing, ready to fly again. The payload separates, and suddenly there is silence. Not the silence of the ground, not the familiar silence of a quiet room or a still night. The silence of space, which is not the absence of sound in the way that a soundproofed room is the absence of sound. It is the absence of the medium through which sound travels. There is nothing for vibration to propagate through. The mechanical universe of the rocket, the turbopumps and the combustion, and the structural resonance and the vibration transmitted through every bolt and every weld, ends at the separation pyrotechnics and does not exist on the other side. For the spacecraft, the separation is the transition from passenger to principal. Throughout the launch, the payload has been cargo, something the rocket was carrying, subject to the rocket's trajectory, accelerations, and vibrations, protected inside its fairing, passive. At separation, the spacecraft's own systems take over. The power goes from pre-separation mode to post-separation mode. The antennas that were stowed for launch deploy. The solar panels that were folded unfold and orient toward the sun. The first downlink signal arrives at the ground station. The spacecraft is now in free fall. Not the momentary weightlessness of an aircraft in a parabola, but the permanent free fall of orbital motion. The spacecraft and everything inside it falling continuously toward the Earth and continuously missing it at the same rate. Every loose object floats. Every liquid forms spheres. The human body, if there is a crew, and feels its own weight not at all. This condition, weightlessness, or more precisely microgravity, is not the absence of gravity. Gravity at the altitude of the International Space Station is approximately 90% of its surface value. The station is deeply inside Earth's gravitational field. It is weightless because it is in free fall, and everything inside it is falling with it. The astronaut floating in the corridor of the station is not experiencing reduced gravity. They are experiencing the absence of the surface pushing up against their feet. The orbit the spacecraft now occupies will carry it around the Earth once every 90 minutes if it is in low Earth orbit, once every 24 hours if it has been placed in geostationary orbit. The altitude at which the orbital period matches the rotation period of the Earth, and the satellite appears stationary above a fixed point on the surface. Weather satellites, communications satellites, navigation satellites, the infrastructure of the modern world that relies on space, orbits at various altitudes for various reasons. Each orbit a different compromise between coverage, signal strength, radiation environment, and launch cost. The separation event itself takes a fraction of a second. The pyrotechnic separation devices, small explosive bolts or release mechanisms, fire. The mechanical connections between the rocket and the spacecraft are severed, and the small springs or gas systems built into the interface push the spacecraft gently away from the spent rocket stage. The relative velocity at separation is a few meters per second. Slowly, the stage and the spacecraft drift apart. The stage, deorbited by a planned engine burn or left to decay naturally, will re-enter the atmosphere. The spacecraft moves on. The mission that the rocket existed to make possible, now beginning. In the silence where the rocket was, moving at 7.8 kilometers per second, falling forever around the Earth, in absolute quiet. The launch pad at dawn is a different place from the launch pad at night. The night pad was alive with intention. The floodlights, the venting cryogenics, the crawler transporter, gone, but its weight still visible in the impressions left on the crawlerway, and the countdown running in the launch control room across the flat Florida landscape. The structure had the specific quality of something about to do the most energetic thing it will ever do. The rocket stood in the light with all of that potential in it. The dawn pad has been through it. The hold-down arms that gripped the Saturn V or the Falcon 9 stand in their released position, the metal showing where the mechanism engaged and disengaged. The flame trench, the concrete channel below the launch platform that directs the engine exhaust away from the structure, is scorched and washed by the water deluge system that floods it during ignition to reduce the acoustic energy reflected back up at the vehicle. The scattered debris of launch, the ablative material shed by the vehicle during the first seconds, are the fragments of the pyrotechnic release mechanisms, the residue of the sound suppression water turned to steam, the gantry, the service structure that surrounded the rocket in the days of pad preparation, stands empty. The umbilicals that fed propellant and power and coolant to the vehicle have been retracted. The white room at the crew access arm, through which astronauts boarded the capsule in the final hours before launch, is swung away. The access arm itself is folded back. What left this pad is, right now, either in orbit or has been in orbit and has returned, or is on its way somewhere farther. The mission that required all of this infrastructure, the months of vehicle stacking and system testing and countdown dress rehearsals and weather scrubs and final launches, is underway, sustained now by physics rather than by the pad. You have spent tonight inside the mechanics of this. You know now that the rocket works in a vacuum because it carries its own reaction mass, and that Newton's third law requires no medium to be pushed against, only mass to expel, and a direction to expel it. You know that Konstantin Tsiolkovsky derived the equation governing this alone in a wooden house in Kaluga in 1903, before the Wright brothers flew. You know that Goddard's rocket Nell rose 41 feet on March 16th, 1926, into a snowy field in Massachusetts, and that no newspaper thought it worth reporting. You know that the combustion chamber wall is kept below its melting point by the cryogenic propellant flowing through it before it burns. You know that the de Laval nozzle converts 2% efficiency to 64% by accelerating the exhaust through a convergent-divergent throat to supersonic speed. You know that the Saturn V first stage burned for 161 seconds, produced 34.5 million newtons of thrust, the equivalent of 85 Hoover dams, and then fell into the Atlantic, its job complete, to be used once and never again. You know that orbit is not a place, but a way of falling. That the thin blue line of atmosphere at the limb of the Earth is all that separates the surface from the void, and that, from orbit, it looks disturbingly thin. That the plasma sheath of re-entry reaches over 1,600 degrees Celsius and blocks radio contact for several minutes, and that the flight controllers wait in silence until the signal returns. Before you close your eyes tonight, one small thing that means a great deal to this channel. Please hit the like button and subscribe if you haven't yet, because tomorrow night we will be here again with another story built for exactly this hour. Your place is kept, but for now, the pad is quiet. The structure stands in the early light. The flame trench is cooling. The thing that stood here last night is somewhere overhead, moving at 7.8 kilometers per second, falling around the Earth in silence. And the day that comes after the launch is always the quietest day at the pad. The launch accomplished, the pad at rest, the sky above it empty and clear. Sleep well.